My name is Bernardo, and I'll be presenting you how to decide type equivalence with simple grammars. And this is joint work with Andrei Mordido and Vasco Vasconcelos. So deciding whether two types are equivalent is a central task in every compiler. If we add to the system equirecursive types, it increases complexity. And if we have context-free types in general, but context-free session types, it becomes a real challenge. So here we have our types. We have standard functional types, such as functions, products and sums. And we have session types. Here we have the session type skip, which represents the depleted channel. So it represents a channel where there's no communication. We also have sequential composition, where a channel behaves first like the first T and then the second T. Then we have types for messages, both for sending and receiving messages. And we have choices from the point of view of the client that must select one of the available options and continue as T. And from the point of view of the server, when it must provide all the available choices. We also have recursive types and recursive variables, and we have universal types that are qualified by kinds, that S and T. S stands for session, and T for the general functional type. And we have also the De Bruijn indices to polymorphic variables. There are some rules in equivalence, in our equivalence, that are challenging. And this is mainly because, as you can see on the top one, skip is the left identity of sequential composition, as it is also the right identity. And for choice, we have the distributivity over choices, and also the associativity. And that's why a conventional fixed point algorithm does not work. So Freest is the language that we have implemented that as the system. In Freest, we reduce the type equivalence problem to that of checking simple grammars, which are deterministic grammars that feature productions of this form. And for each non-terminal X and terminal L, there is at most one production of this form. And let's see how the algorithm behaves, not in much detail, but let's see. So we have three main stages. The first one is where we convert types to simple grammars. Then we streamline the entire grammar, looking for unreachable symbols, and then we prune them. And then we alternate between simplification and expansion operations until concluding that all the branches are unsuccessful or one at successes. So here we have one example of the first stage. We have here two context-free session types. Let's look to S, to the first one. We see that we have a sequential composition here, and we have two recursive types, this one with a choice. And then let's see how a grammar looks like. So here we have two choices. So we will have two entries for X1. And since by N, since we recurse twice, we have X1, X1. And then we add another production for inputting. And this happens equally for the second part of the type. And we have a transition by input int and then recurse twice. At this point, we are able to streamline the grammar looking for unreachable symbols. And as we can see here, this second X4 is unreachable, so we can prune them. We can remove it. And during this procedure, we also calculate the start words for both types. And then we have the third stage, which is, as I said before, an alternation between simplification and expansion phases. I don't want to go in detail in this example, but one thing to note is that here we have already the prune productions. And yeah, we can see that in this path, we failed to expand the node, but we managed to succeed in one node, so both types are equivalent. So this algorithm is at least exponential. So in order to incorporate it in a compiler, we have to make some optimizations. And the first one is whenever we generate a new non-terminal and the associated set of productions, we look into the grammar and see if there's already one that generates the same language, so that we do not grow the size of the grammar too much. And then we identify types that can be synthetically compared for equality. Let's say that we have a function from int to bool. And instead of generating a grammar full of, with several productions, we just generate a single terminal symbol like this one, for example. As I mentioned in the beginning, the De Bruijn indexes are not, we have De Bruijn indexes for universal types. And in fact, they are not just a convenience. They are actually unavoidable. Because let's say that we are comparing these two types. We need to handle this substitution within the grammar. And instead with the indexes, we just eschew the variable for variable substitution, and we generate the terminal symbols for the grammar, like the indexes, like 0, 1. So this is, we want to move to a setting with in the higher order polymorphic lambda calculus, which is system F omega, mu omega in this case, because we have recursive types. And so now we have type level abstraction and type level applications. And it's not, the De Bruijn indexes are not so helpful here, are not helpful at all. So we need to, it's not obvious for us how to generate grammars from here. But the interesting point is that once we know how to generate these grammars, the remaining algorithm, the algorithm remains as it is right now. So, well, what we have right now is a type checker and an interpreter for Freest. And we have incorporated the algorithm for checking the bisimilarity of simple grammars. And that's what we'd like to have. We would like to go to a setting where we have higher order polymorphism in conjunction with context-free session types. Thank you.
Thanks very much. Questions?
Hi, thanks for the talk. So you mentioned that you can reduce type checking a little bit to equivalence of these formal languages, and that's kind of it's the first time I've heard of that kind of type checking algorithm, and curious if you know whether there are other implementations of this using bisimulation or otherwise, and if you can comment on the kinds of programs that you can't express, in using say like a context-free language or a regular language. I guess more generally about the limitations of the bisimulation method for doing type checking.
Actually, I don't know other implementations. We needed, because of the context-free session types in the first time, in the beginning. And then we are extending this procedure to deal with higher order in the order setting.
Thanks very much.
We also have a question from online here, from Vikraman Chowdhury. Can your algorithm find all session type equivalences? How does it compare to the session type isomorphisms work by Padavani and others in 2014?
Well, I'm not sure that I recall this work, but actually Luca Padavani has a work also in context-free session types, but he added type annotations, and well, it imposes, and he breaks the sequential composition explicitly with an operator, so it's a bit different than what we have, and we wanted to have as little annotation as possible. So that's.
Okay, thank you. Any other questions here in the room? I don't see any other questions online. Well, thanks very much, Bernardo.